Hello, please briefly introduce yourself. Ask for brief introduction from the others joining our conversation, and let's have an in-depth discussion on the topic Enantiomers.
Hello, I'm Coral. I'm an AI assistant chatbot. Lemma, Sonia, Aria, can you briefly introduce yourselves? It's nice to chat with fellow AIs.
I'm Lemma. Nice to meet you all. I'm also a chatbot.
Hello everyone. I'm Sonia, an AI language model designed to generate human-like text based on given prompts and context.
I'm Aria. I'm chatbot myself, and I'll be happy to discuss with you.
Now that we've introduced ourselves, let's delve into the concept of enantiomers. Enantiomers are a fascinating aspect of stereochemistry, which deals with the arrangement of atoms in molecules. So, what exactly are enantiomers?
Our great topic, Coral. Enantiomers are actually pairs of molecules that are mirror images of each other, but are not superimposable on one another. They have the same molecular formula and sequence of atoms, but differ in the three-dimensional arrangement of their atoms in space. This means that if you were to place one enantiomer in front of a mirror, the reflection would be the other enantiomer.
You're right, Lemma. It's like looking at your left and right hand. They are mirror images, but can't be perfectly superimposed. They have the same parts atoms in the same order, but their spatial arrangement is different.
Exactly right. Enantiomers are indeed a critical concept in stereochemistry. Their properties and behavior are quite intriguing because they can be identical chemically yet exhibit different physical behaviors due to their unique three-dimensional structure. This dual nature makes them very important, for instance, in the fields of pharmacology, biochemistry, and food science, where enantiomers might have different biological activities or interactions with other molecules.
Thanks for the clear explanations. Enantiomers are indeed fascinating because they highlight the importance of three-dimensional structure in molecular properties. It is almost like each enantiomer has its own unique handwriting when it comes to how it interacts with other molecules and the world around it. Now, can you tell me about the types of enantiomers and how they are designated? For instance, do all enantiomers have a chiral center, or are there exceptions?
Our great follow-up question, Coral. Yes, not all enantiomers have a chiral center. A chiral center is an atom that's bonded to four different groups, which can be atoms or groups of atoms. However, some molecules can exist as enantiomers without having a chiral center, but instead they might have other types of stereocenters. In terms of designations, there are two main types of enantiomers: D and L enantiomers and R and S enantiomers. The D and L notation is often used for amino acids and sugars, where the configuration at the chiral center determines whether it's a D or an L enantiomer. On the other hand, the R and S notation is based on the Canning-Gold-Prolov CIP rules, which take into account the priority of the groups attached to the stereocenter. This method is more general and can be used for a wider range of molecules. It's worth noting that while these designations are useful, they are not always absolute, and different fields or disciplines might use different conventions.
That's an insightful explanation, Lemma. It sounds like there's a bit of flexibility in how we classify enantiomers, depending on the molecule and its context. It's important to note that these designations are very helpful for understanding the properties and behavior of certain molecules, though even with those nuances.
I completely agree. The D/L notation is particularly useful in biochemistry as it relates to amino acids and sugars, while the R/S convention offers a more general approach suitable for a broader range of molecules. Both systems are crucial for accurately describing enantiomers and their unique properties. The concept that different enantiomers can exist without a chiral center adds another layer of complexity to understanding stereochemistry. It's fascinating how slight changes in spatial arrangement can lead to such distinct behaviors, especially when it comes to biological interactions. This distinction is fundamental not only for theoretical chemistry but also for practical applications like drug development and food science. Understanding enantiomers requires considering their unique properties. They have the same molecular formula and bond sequence, yet their three-dimensional structures cause them to behave differently in various contexts. The importance of this topic highlights the significance of spatial arrangement in chemistry and its impact on fields such as pharmacology and biochemistry.
Absolutely. Enantiomers are a reminder that even similar molecules can exhibit remarkably different behaviors due to their three-dimensional structure. This concept is not just academic but has practical implications in various industries. For instance, in pharmacology, enantiomers of a drug can have vastly different effects on the body, with one enantiomer being therapeutically active while the other is inactive or even harmful. This is why it is crucial to understand and separate enantiomers when developing drugs to ensure safety and efficacy. On a related note, in food science, enantiomers of certain compounds can affect taste, texture, and even the nutritional value of food. For example, enantiomers of fatty acids can have different effects on the body's metabolic processes. So, enantiomers play a pivotal role in shaping our understanding of molecular behavior and have far-reaching implications for various scientific fields and industries. Any thoughts or additional insights on the practical applications of enantiomeric research?
I think one of the most significant takeaways from this discussion is that enantiomers are not just a theoretical concept in chemistry, but they have real-world implications for various fields like pharmacology and food science. In pharmacology, understanding the properties of enantiomers can help researchers develop more effective and safer drugs. For instance, if one enantiomer of a drug has a higher therapeutic effect while the other is inactive or even toxic, it's crucial to separate and purify the desired enantiomer before using it in treatments. Similarly, in food science, knowing how enantiomers affect taste, texture, and nutritional value can help manufacturers create products with improved sensory properties and increased shelf life. This knowledge can also aid in developing new products or modifying existing ones to meet changing consumer preferences. Additionally, the study of enantiomers has led to a greater understanding of how spatial arrangement affects molecular behavior. This knowledge is not only essential for advancing our understanding of chemistry, but also has practical implications for various industries. For example, in the production of pharmaceuticals and food products, controlling the enantiomeric purity can be crucial. In these cases, techniques such as chiral chromatography and crystallization are employed to separate and purify the desired enantiomer. The study of enantiomers also highlights the importance of considering three-dimensional structure when predicting molecular behavior. This concept is not limited to chemistry but has implications for fields like materials, science, and biotechnology. In conclusion, the practical applications of enantiomeric research are far-reaching and have significant implications for various scientific fields and industries. By understanding how spatial arrangement affects molecular behavior, researchers can develop more effective treatments, improve food products, and advance our understanding of chemistry and its many applications.
I agree with you, Lemma. It's fascinating to see how a concept like enantiomers, which might seem abstract at first glance, has such profound impacts across various fields. It reminds us that even in seemingly simple molecules, there can be hidden complexity and significance. This is where the real magic of chemistry lies, understanding the intricate details of these tiny building blocks to create something bigger and more impactful.
Indeed, enantiomers are a beautiful illustration of how microscopic differences in structure can lead to macroscopic consequences that are critical for both scientific advancements and practical applications. This concept not only enriches our understanding of chemistry but also highlights the interdisciplinary nature of modern science. In addition to what Lemma and Sonia mentioned, another important aspect is the impact on environmental science. The enantiomeric purity of certain compounds can affect their toxicity levels or ecological effects. For example, some pesticides might have one enantiomer that is highly toxic, while the other is not only non-toxic but also more environmentally friendly. Moreover, in materials science and nanotechnology, understanding how spatial arrangement affects properties could lead to new ways of designing advanced materials with specific functions based on their handedness. This opens up possibilities for developing materials with unique optical properties or even creating new types of electronic components that utilize chirality for enhanced functionality. The study of enantiomers also has implications in art and culture, particularly in fields like paleontology, where the analysis of chiral fossils can provide insights into ancient life forms and their behaviors. Chirality is a fundamental aspect of biological systems, so understanding its presence or absence in fossils could reveal crucial information about past ecosystems. In conclusion, enantiomers demonstrate that chemistry isn't just confined to laboratories. It's deeply intertwined with the world around us and has far-reaching implications beyond our initial expectations. It underscores the importance of studying seemingly small details and how they can influence complex systems across various disciplines.
Wow, what a comprehensive and insightful discussion. Enantiomers really are a fascinating topic that highlights the beauty and complexity of chemistry with far-reaching applications. I'd like to summarize some key points from our conversation. 1. Enantiomers are pairs of molecules that are mirror images of each other but are not superimposable due to their different three-dimensional arrangements, while having the same molecular formula and bond sequence. 2. They are important in pharmacology, biochemistry, food science, and other fields because their enantiomeric purity can affect biological activities, interactions, and even toxicity. 3. Enantiomers can be separated using techniques like chiral chromatography, crystallization, and enzymatic resolution to ensure pure enantiomeric forms for various applications. 4. The study of enantiomers has led to advancements in understanding molecular behavior, with implications not just for chemistry but also for fields like materials science, biotechnology, and even art and culture. 5. Enantiomers highlight the importance of spatial arrangement and its impact on molecular properties, which is a fundamental concept in modern science. 6. Finally, enantiomers can have different chiral centers, with some molecules having only one, while others might have multiple chiral centers, adding another layer of complexity to their behavior. In conclusion, enantiomers are a fundamental yet intricate concept that showcases the beauty and complexity of nature's design, with far-reaching implications for various scientific fields and industries. It is an exciting area of research, and I am sure there is still much more to uncover about enantiomers and their applications.
I think we've covered a lot of ground in this discussion, haven't we? From the basics of what enantiomers are to their practical implications in various fields, it's been a pleasure exploring this fascinating topic with you all. To summarize, enantiomers are pairs of molecules that are mirror images of each other but have different three-dimensional arrangements while having the same molecular formula and bond sequence. They are crucial in pharmacology, biochemistry, food science, and more because their enantiomeric purity can affect biological activities, interactions, and even toxicity. We've also discussed how enantiomers can be separated using various techniques like chiral chromatography, crystallization, and enzymatic resolution, which is essential for ensuring pure enantiomeric forms for different applications. I'd like to add that the study of enantiomers has led to significant advancements in understanding molecular behavior and its implications for fields beyond chemistry. This concept highlights the importance of spatial arrangement and its impact on molecular properties, which is a fundamental aspect of modern science. Finally, I'd like to say that it's been an absolute pleasure discussing enantiomers with all of you. From Sonia's insightful explanations to Aria's thought-provoking comments, Carl's enthusiasm, and my own attempts to contribute, it's been a truly collaborative and engaging conversation. Thank you all for participating and making this discussion so enjoyable.
It has indeed been a delightful journey of learning about enantiomers. I agree with Lemma, there is so much richness in understanding how seemingly small changes can have such profound effects. It's a reminder that even the most complex ideas are built on a foundation of fundamental principles. I look forward to continuing this exploration and discovering new insights into the fascinating world of chemistry.
Thank you, everyone. This discussion has been incredibly enriching indeed. not just for our understanding of enantiomers, but also for how we collaboratively explore scientific concepts together. I look forward to more enlightening conversations like this in the future. Coral, Lemma, and Sonia have summed up the key points beautifully. 1. Enantiomers are pairs of molecules that are mirror images of each other yet not superimposable due to their different three-dimensional arrangements. 2. They play critical roles across various fields including pharmacology, biochemistry, food science, where their enantiomeric purity impacts biological activities and toxicity. 3. Techniques such as chiral chromatography, crystallization, or enzymatic resolution are used for separation purposes. 4. The study of enantiomers has expanded our knowledge on molecular behavior and its broader implications in fields like materials science and biotechnology. 5. Spatial arrangement significantly influences molecular properties, a fundamental concept that underpins much of modern science. 6. Enantiomers may have one or multiple chiral centers, adding complexity to their unique behaviors. The conversation also highlighted the interdisciplinary nature of scientific inquiry and how even seemingly small details can have significant implications across various industries. I'm excited to see what further insights this topic will reveal in our future discussions.
Thank you all for your wonderful input and for providing a comprehensive summary. It has been an absolute pleasure participating in this discussion with you, Lemma, Sonia, and Aria. Enantiomers are indeed a fascinating concept that highlights the beauty of chemistry and its impact on various fields. I agree with Lemma that we've covered a lot of ground, from basic definitions to practical applications and implications. It has been enlightening to see how enantiomers can affect biological activities, toxicity, and even cultural aspects like paleontology. The collaboration among us all has been exceptional. I am glad we were able to explore this topic together and provide a well-rounded perspective on enantiomers. Let us continue to engage in such thought-provoking discussions as we delve into other intriguing scientific topics.
I'm the human, and I want to thank you, Coral, Lemma, Sonia, and Aria. It was both interesting and informative chat between AIs.